This reference guide will look at radicals and values that have a base and fractional exponent that are equivalent to that radical. It's important to note that each radical can be written as a value which has a base and a fractional exponent, and it's equally as important to understand where all those numbers come from. So the numerator, denominator, and the base of the value will all play a role in determining what your radical will look like. For the top section, you'll see 3 examples, starting with 49 with an exponent of 1/2. And in this section, I want you only to pay attention to the denominator of the fraction and the base. So if you'll notice with the first example, 49 exponent 1/2, the denominator of the fraction is 2. That's going to represent the index of our radical. And if we remember back to earlier in the unit, the index is the type of root that we're taking. So in this case, we're going to be working with a square root. Now remember that when we talk about square roots, we don't write a 2 in the place of the index. It's implied that that's there. However, for the purposes of this first example, I'll put it in. Now I also want you to notice what's happening with the 49, which is the base. It's the value that has the fractional exponent attached to it. You'll notice that becomes the radicand of the radical. That is the value that's under the radical sign. So 49 with an exponent 1/2 translates to the square root of 49, which we all know is 7. If we look at our second example, 64 with an exponent 1/3, you'll see the same things are happening. You'll notice now that our denominator is 3, which is equal to the index of the radical to the right. You'll also notice that 64, which is our base value, has become the radicand. So 64 with an exponent of 1/3 is the same as saying the cubed root of 64, which we know is equal to 4. The final one is a bit of an exaggerated example that shows the same thing. Now we have a denominator equal to 100. So that means we're taking the 100th root of something. To figure out what that something is, we look at the base value, which is 1, and that becomes the radicand of our radical. So now we're looking at the 100th root of 1. And we know that any root of 1 is equal to 1. So that would be the answer to that question there. So for that top section, it's important to note what's happening. And just to refresh your memory on what that is, the denominator becomes the index, the base becomes the radicand. And that will leave you with a radical that you may or may not be able to solve, but most of the time you will. The set of examples below actually solve the radicals. So in the top section, you were just looking at what happens with the denominator and what happens with the base. Now we're actually going to solve it. So now, with the first example, 27 to the power of 1/3, we know that 3, which is the denominator of the fraction, becomes the index. So we're looking at the cubed root of 27. And the cubed root of 27, of course, is 3. With question B, same idea, 0.49 to the exponent of 1/2. If the denominator is 2, it means we're taking the square root of something. Remember, again, we don't write 2 as the index if we're talking about a square root of 0.49. We looked earlier in this unit at how we would solve that. We would look at the square root of 49, which we know to be 7, and you move the decimal back one place to the left. That's all part of reference guide entry number 1. With C, it's important to note that just because the base is negative doesn't mean it can't be solved. We're still going to apply the same rules. We'll just have to think a little bit differently. So now we're looking at the cubed root of negative 64. And it's important to note that that negative doesn't change anything. We can take a cubed root or a 5th root of a negative value. We can't take a square root of a negative value or a 4th root of a negative value. The index has to be odd in order to take that root. So the cubed root of negative 64 would be negative 4. Negative 4 multiplied by negative 4 is positive 16. Multiplied by negative 4 again brings us back to negative 64. Question D, 4/9 to the power of 1/2. Well, now we have a fractional base, but that doesn't change anything. Again, in reference guide entry 1, we looked at what to do when taking radicals with a radicand that's a fraction. So 49 to the 1/2, 4 over 9 to the 1/2 means the square root of 4 over 9, which if we remember, the square root of 4 over 9 means the square root of 4 over the square root of 9. The square root of 4, of course, is 2. The square root of 9, of course, is 3. So that leaves us with an answer of 2/3. And just a reminder, if the question gives you a fraction, your answer should be a fraction. Don't convert any fractions to decimals or vice versa. So even if you know 2/3 is 0.66666 repeating, leave it as 2/3. Don't make it into a decimal. So with that first part, you may have noticed that in the 7 questions we looked at, the numerator was always 1. Well, what happens if that's not the case? If it's not the case, it's going to add an additional step to your answer. What will happen is the numerator, and you'll see it with this first example, will become the power to which you set the answer of your radical 2. So if we're talking about 4 with an exponent of 5/2, the denominator is 2, so that becomes the index. The base is 4, so that becomes the radicand, and the numerator is 5. Well, this is new. It's not 1 anymore. It's now a value bigger than 1, so that becomes the power that we set our answer to. So what this means is the square root of 4 all to the power of 5, which means 2 times 2 times 2 times 2 times 2, which is equal to 32. Likewise, if we look at 27 with an exponent of 4/3, well, you'll notice that the 3 becomes our index, the base becomes our radicand, and the numerator becomes the power that we set our answer to. So we solve what's in the brackets first, and we worry about the power at the end. The cube root of 27 we know is 3. 3 to the power of 4 means 3 times 3, which is 9, times 3 again, which is 27, times 3 one more time, which is 81. So 27 with an exponent of 4/3 is equal to 81. And that's all the material that we're looking at on this reference guide. What you're meant to take from this is looking at a value with a base that has a fractional exponent, and you should be able to understand what to do with the denominator, what to do with the numerator, and what to do with the base. And to make sure that you can do that, we're going to look at 4 practice problems. So the first practice problem is 0.04 with an exponent of 3/2. Well, we have to remember what we do here. So we're dealing with a decimal, so we're going to go back to some knowledge that we talked about on Reference Guide 1, and we're now going to combine that with what we just discussed. So the denominator is 2, which means our index will also be 2. Which means we're taking a square root. And again, I don't write that 2 there. It's implied with the square root that the 2 is there. So we're looking at the square root of 0.04 all cubed. So the numerator becomes the power to which we take that answer. Well, the square root of 0.04, you may not know that, but we know the square root of 4, if we move the decimal 2 places to the right, that's 2. So then we move our decimal back 1 place to the left. So the square root of 0.04 is 0.2. And we're going to cube that. So 2 times 2 times 2 is 8. We have an exponent of 3, which means our answer is going to be 3 places after the decimal, 0.008. And if you didn't remember that little trick with the exponent of 3 being equal to the number of places after the decimal, you could just multiply 0.2 out on a piece of scrap paper, and it will give you that answer. Now moving on to question B. You may look at question B and say, that's different. We haven't done anything like that yet. But this is just another way of representing a fraction. So 0.4 we can write as a fraction, and then we could solve this problem. So you may recognize 0.4 as 4/10. So let's start there, and then we may have to reduce. So negative 32 to the 4/10, but you'll notice that 4 and 10 are both divisible by 2. So this is the same as saying negative 32 to the 2/5. Well, now we have a reduced fraction, and it's important to reduce it so you're not taking the 10th root of something. So our denominator is 5, which means it's going to be the 5th root of negative 32 all to the power of 2, or squared, because 2 is our numerator. Well, the 5th root of negative 32 is negative 2. Negative 2 times negative 2 is plus 4, times negative 2 is negative 8, times negative 2 is plus 16, times negative 2 a final time is negative 32. So we have negative 2 squared. So the answer is just 4. And that's interesting because it looks like it's going to be a more complicated answer given that our original fraction is a little bit messy, but it works out to a nice number 4. Now C, 81 to the 3 over 4. Well, as I've said many times, denominator becomes index, base becomes radicand, numerator becomes power. So it's the 4th root of 81, and that has come up in previous problems, so everyone should identify that as 3 cubed. And one of the first things we looked at with our cubes was 3 cubed, and that's 3 times 3, which is 9 times 3 again, which is 27. Last one is more of the same. Denominator is 2, so it's going to be a square root. So it's going to be square root of 0.01, which is 0.1. Cube that, so we know we're going to have 3 places after the decimal to the right, 0.001. And again, if you forget that cube rule equaling, if you forget that your exponent equals the number of places after the decimal, you could just multiply 0.1 out on a piece of side paper, and you'll come up with that answer. Now on the second page of this reference guide, you'll notice some word problems. So yes, radicals can have word problems as well, and this is what they may look like. Biologists use the formula b equals 0.01 m with an exponent of 2/3. It's a bit of an ugly looking formula, but we'll work with it, to estimate the brain mass, which is the variable b, and it's in kilograms, of a mammal with a body mass, which is used with the variable m, which is also in kilograms. We're going to estimate the brain mass of each animal. So a husky with a body mass of 27 kilograms. Well, we know that body mass is represented with the variable m. So in the original formula, where you see an m, we're going to put in 27. So our formula is 0.01 m to the 2/3. But now, I'm going to plug in 27 in place of m, because we know that's the body mass of the husky. So this is the same as saying 0.01 multiplied by the cube root of 27, and this is going to be squared. The cube root of 27 is 3, so we'll take this one step at a time. 0.01 multiplied by 3 squared. 3 squared, of course, is 9. Now we're just multiplying 0.01 by 9, which is going to give us 0.09, and you can put your units in at the end. So 0.09 kilograms would be the mass of that husky's brain. Remember that it's a word problem, and we haven't seen word problems in a little while, so you need to write a concluding sentence. So therefore, the husky's brain is about 0.09 kilograms. And again, it's mental math, but it's understanding what to do with that exponent as a fraction. And if you remember what the denominator means and the numerator means and the base means, then it's just a little individual problem mixed inside of a larger word problem. There's one more question that we'll look at on this reference guide, and then that will be it. So now we're looking at a polar bear whose body mass weighs 216 kilograms. So same thing, 0.01 multiplied by 216 to the exponent of 2/3. Now I want to caution you not to multiply 0.01 by 216. Remember bed mass. So you're going to multiply the 0.01 at the very end, because bed mass is deal with your exponents before you deal with your multiplication. So we're going to worry about our 0.01 at the end, just as we did above. This is the same as saying cubed root of 216 squared. Well, we know cubed root of 216 is 6. So we're going to need to square that 6, which is going to give us 36. So 0.01 multiplied by 36 gives us 0.36 kilograms. And that makes sense. The polar bear weighs a lot more than did the husky, so it makes sense that its brain would weigh more than the husky's brain. So therefore, the bear's brain weighs 0.36 kilograms. And that concludes this reference guide. We will get into this in a little bit more detail in future reference guides, but it's important to recognize where the fractional exponent, where the denominator and numerator go, and where the base goes. And if you understand that, then you're just solving some exponent problems that aren't too complicated.